Thank you. Thank you, Marcus and Mauricio. He's not here. For organizing this very nice summer school, I learned a lot. As for neutrinos, I'm also a starter. Even I have been a postdoc here, but I'm still starting for neutrinos. My main research interest on the high energy astrophysics, but luckily I found I have a few works on gamma ray burst neutrinos, and nobody has covered this topic in this group, in this school, I guess. So I'm very lucky. But first of all, let me make a very brief introduction to the gamma ray burst. So the gamma ray burst was yes, can you say this? The gamma ray burst was discovered in 1960s and is discovered by a military satellite. It's launched by US to monitor the nuclear weapon experiments to the other country. And then finally, they found some signals from outside the Earth. And initially, maybe they becomes very worried about that, but finally, it turns out it's not a man-made signal. It's the gamma ray signals last for seconds, and then it's originated from outside the Earth. And for the history of gamma ray burst, you can divide it roughly into different areas based on the highlighted satellite used to monitor gamma rays. And at the very beginning, because the sensitivity of the detector is not good enough, so there's not only a burst of gamma rays, but also a burst of theoretical models. People know nothing about that until later at stage 2 or stage 3, the general models become settled down. And right now, we can have 1 to 3 GRBs detected per day. It's a very high event rate. In stage 2, the very famous instrument, BAS, they detected 2,700 gamma ray burst. And if you point the direction of each burst onto the scan map, you found it's nearly isotropic. That means it may have an extragalactic origin because it's not focused on the Milky Way plane. And then they have a good sample of gamma ray burst, and they can have a statistics on the duration of the burst. And they find some very clear separation between 2 seconds. So they divided the gamma ray burst into long gamma ray burst and short gamma ray burst. So it indicates they should have different types and maybe different origins. Later in stage 3, because we have a more follow-up telescopes, and we can observe the gamma ray burst from different wavebands. Most interesting is X-ray band or optical band. The joint detection was achieved at that time, and then that means the GRBs not only have gamma ray radiation, but also multi-wavelength radiations. And with the optical observations, we can try to find the line structures on the spectrum. And with that spectrum, we can estimate the distance of the gamma ray burst. And with the flux and distance, we can calculate the total energy budget. So with the cosmological distance, the total luminosity, isotropic gamma ray luminosity, is about 10 to 41 erg per second. Maybe you don't have a very good feeling of this amount of energy, but if you compare to our sun, the sun can release this amount of energy during its whole life. And gamma ray burst can reduce this energy in 1 second. So it's extremely powerful. And later, the detection between gamma ray burst and supernovae, the long gamma ray burst and supernovae, and they confirms the origin of long gamma ray burst is from the collapse of massive stars. And until 2017, when people have the joint detection of the gravitational waves from binary neutron star mergers, and also together with the gamma ray burst and the kilonovas. Until that time, they come from the region of short gamma ray burst. It comes from binary neutron star mergers. At least some of them comes from binary neutron star mergers. Okay, if you go into more details, we consider a very short duration of the gamma ray burst and very energetic. You can estimate the radiation region size from the duration times the speed of light. So this is the region where the gamma rays was released. And that region is relatively small. And you have a very powerful gamma ray emissions. That means the gamma ray photons the density is very high in that region. So that causes a problem. The gamma-gamma interaction will happen in this very optical depths, very optically thick region, and the gamma ray photons cannot be released. But to solve this problem, we need to introduce the relativistic motion of the GRB ejector. So if you have a relativistic motion and what we observed is already boosted, the photon energy is boosted. So in the co-moving frame of the ejector, the photon energy was just X-rays, not gamma rays. And then we have fewer photons that can satisfy the gamma-gamma pair production conditions. And also in the co-moving frame, the size of the radiation region is larger because of the relativistic motion. And then finally, we have a correction factor for the optical depth of relativistic case. Is gamma to the minus 6.4. And if you have a gamma like a few hundreds, then this can reduce the non-relativistic optical depths in the to close to 1 or smaller than 1 in the relativistic case. So that solves this problem. And why I said it's a jet? The jet is because people observed some break structures in the afterglow of GRBs, because the afterglow depends on the kinetic energy of the GRB ejector, and it's decaying because the ejector was decreasing, it's decelerating, and at the beginning, only the light from the 1-hour gamma cone can be observed, and during its decrease, and more light will go to the observer. And that's why initially it was decaying, but the decay was shallow because you have this 1-hour gamma effects. But when this 1-hour gamma cone can cover the whole opening angle of the jet, then no more light will go to the observer. So the decay becomes steep. So observation of this break confirms that it comes from a jet, relativistic jet. Okay, right now it seems that everything has settled down, but the most important part is still under debate. Where and how does the gamma rays generated? There are still 3 models survive right now. The first model is dissipative photosphere model. They have a lot of dissipations happens below the photosphere, and they accelerate particles and generate gamma ray emissions. And the gamma ray photons can be released at the photosphere. And the internal shock model allows the collisions of different shells of the jet happens beyond the photosphere, and they can produce gamma rays and immediately release. And another model is have a larger radiation radius. Like this is the ICMARC model, internal collisional induced magnetic reconnection and turbulence. They have a lot of in this model, they assume the jet was dominated by magnetic field, and the reconnection happens in a very outer regions. So if you look at this three different models. They predict different radiation radius. That means you will have a different number density of particles and photons. So the interaction between particles and photons will have a different in efficiency, and so they will emit different flux of neutrinos. So we could use the neutrino signal to help differentiate these different models. That's important. And before I go to the flux, I want to make a very quick estimation on the neutrino energy. Here we consider the p-gamma interaction because gamma bursts have a lot of gamma rays. So, and then we have accelerated particles. When their energy satisfies the delta resonance condition, then they will produce charged pions, and charged pions will further decay to neutrinos and leptons and electrons, positrons. And then typically, each pions will carry 1/5 of the proton energy, and each lepton shares 1/4 of the pion energy. So finally, the neutrino energy would be 1/20 of the proton energy. And from the gamma ray energy and the model predicted some predicted the Lorentz factor of the jet, and then we can calculate the corresponding proton energy, and then we find the neutrino energy is roughly at the S cube range. Okay. For and as Maria has talked yesterday, the neutrino spectrum follows the proton spectrum of the proton spectrum and times the efficiency for the neutrino production, and this efficiency proportional to the p gamma optical depths. And for the gamma ray spectrum, it was always described by a band function. It's basically a broken power law. And finally, after some algebras, we find the neutrino spectrum was also a broken power law, but have another broken because of the pion synchrotron coolings. So we will show the spectrum here. And we know the spectrum and how to calculate the flux. And I need to normalize the total flux with the proton energy. Here we have a factor of 1/8. That is half of the protons will go to the first channel to produce neutrinos. That delta resonance is 1/3, but if you consider all the possible channels, it goes to 1/2. And this 1/4 comes from the 4 leptons shares the energy. And then we times the pion production efficiency. This determines, this is basically the fraction of the energy goes to pions and also modified by the optical depths. And how to calculate the proton energy? Then we would have we can estimate it from the gamma ray photon energy by introducing a parameter. It's the energy epsilon E and epsilon P and epsilon E is the energy goes to protons and the electrons, and that energy goes to electrons will further goes to gamma rays. So with this parameter, we can relate the gamma ray energy to the proton energy, and then finally we know the flux and spectrum of neutrinos. And of course, with different prompt emission models, the flux is different. And what we have right now is the ice cube detector, but unfortunately, I'm not a member of ice cube collaboration, so I cannot reach the real-time effect area. But I found some public data from their website, and I suppose it doesn't change too much. And with this effect area, and we times with the neutrino flux and NH integral over NH solid angles and times we can calculate the expected neutrino numbers should be detected. And here we have a very good target. It's the GRB-22109A. It's the brightest gamma ray burst of all time, the boats. And they have a very high isotropic luminosity, 10 to 40, 54 erg per second, and it's very close to us. But even with that energetic burst, IceCube has not detected any neutrino signals, but they put some constraints on the neutrino flux. And based on their upper limit, we can put constraints on our prompt emission models. As I said before, the neutrino flux depends on where the neutrino was produced and where the gamma rays was produced and the Lorentz factor of the jet. And on the parameter plane, we can divide it into the allowed region. There's no neutrino detection is expected, and the ruled out region, we should have detected the neutrinos. And if you look at the photosphere model, which is most close to the central engine, then it's all lies on the ruled out regions. So for this specific burst, the photosphere model should have been ruled out. But for internal shock models, it crossed both the allowed and disfavored region. So in some parameter side with high R and high gamma, then the internal shock models still survive. But for ECMAT models, the ECMAT models have a characteristic radius as 10 to the 15 centimeter. So it's just over here. Most of the space they still survive. And to be more intuitively, we can calculate the expected neutrino flux with some benchmark parameters and with different models, which is the solid line. And we can also calculate the upper limit based on the effective area of the IceCube detector. And you can find for photosphere models and internal shock models, the predict flux has already exceeded the upper limit. So these two models is disfavored. And for ECMAT models still survive. And of course, if we didn't detect anything, we can still put constraints on the parameter of epsilon p over epsilon e that was did from other groups. And what I want to say is this is the best constraints we can have right now because most of the previous works are based on the stacking GRBs. That means you don't focus on one specific target. You search for different GRBs. So the probability to detect at least one association is just a sum of the probability of every single signal. But even with sum up all the GRBs, then it's still the predicted effective flux is still lower than the both GRB. So we cannot provide tighter constraints than both. And then the question comes up, because even it's so bright, we still cannot detect any neutrinos. So how sensitive should a detector be to detect these signals? Here we make a very rough assumption. We assume we have a detector. Its effective area is m times greater than IceCube. And then we can, based on each m value, we can have a detection limit for the boat-like GRB. And the different lines, the solid lines means we put the boat-like GRB at the same distance and same sky location. We put the boat-like GRB at the same sky location as the boat, and these lines means we put it in the best locations. The dashed lines means that's best locations, and we can see even with the this is the redshift of the boat. So as we can see for the photosphere models here, its detection limit is very large. So even with the current ice cube, we can already have a good probability to detect such signals. And for the internal shock model, yes, we can still have a good probability, and we can extend the detecting limit to Z 2.5 if we enlarge the detector with 5 times. And for the ICMAT model, we should increase the factor. We should increase the effect area by 10 times to have a possibility to detect these signals. And we don't always expect the both GRB happens because it's so rare. The event rate is just 1 per 10,000 years. So we should still focus on the stacking GRBs. And with current data and with the ice cube detector, the neutrinos from stacking GRBs by the photosphere and internal shock model should already very close to be detected, but ICMAT model should have a long way to go. And if we increase the effect area by a factor of 5 or 10, and then the dashed line is 5 and dotted line is 10 and solid line is 1. If you increase by a factor of 5 or 10, then the chance to detect the neutrinos from internal shock and the photosphere model is close to 100% with the 5 years data accumulation. And if you consider ICMAT model, you need at least 10 years data accumulation and increase the effect area with 5 or 10 times, and then you have a 35 to 60% to detect the neutrinos from this signal from these GRBs. And what if we still cannot detect anything with advanced detector? And of course, we can put more stringent constraint on the model parameters. And with a greater value of the magnification factor M, and then we can put more and more stringent constraints. The allowed region is just the lower left of this array plots, different models. And the color shows the neutrino numbers. And when it goes to some parameter side that is unreasonable, then we can say that this model is effectively ruled out. For example, the ratio between epsilon p and epsilon e, the fraction goes to protons and electrons, then it's supposed to be greater than 1, but if it's lower than 1, then this model can be effective ruled out. Okay, 5 minutes. Let's get back to the Earth. And what will we have in the future? I guess you are very familiar with IceCube and the IceCube Generation 2 and the KM3 net. And we can find propose the sensitivity curve from their white papers and transfer it to magnification factors defined in our work. And we find that IceCube Generation 2 can effectively increase the effective area with a factor of 8, and KM3 is a factor of 10. And with these detectors, and with 5 years of data accumulation, we can already effectively detect the neutrinos from photosphere or in internal shock models, or maybe ruled out. It depends on whether you detect it or not. But for some extreme parameters in the internal shock models, it still survive. So we need an even larger detector. I guess you never heard of this detector. It's called the Tropical Deep Sea Neutrino Telescope. It was proposed and led by the people from Tengdao Li Institute in Shanghai and some people from Lasso team, and they are planning to put this detector in the West Pacific Ocean, specifically in South China Sea. And it's very ambitious. They said they can enlarge the effective area by a factor of 30. As far as I know, they are considering it seriously. I don't know if it can achieved, but they have doing some very massive experiments, and it can technically it could be as long as they have money. But let's see. Okay, the last part of the talk is when we're talking about the GRBs from gamma ray burst, we cannot ignore the low luminosity gamma ray burst because it have a higher event rate, and maybe they have a higher efficiency to produce the neutrinos, depends on the model. So there are models either from the weak jet or choked jet. Both of these models will predict a very efficient way to generate neutrinos. And if you compare the single chalk jet event with the boat GRB, you found that if they all put it into the same distance, they would predict very comparable neutrino flux. And but the problem is we don't have that sensitive gamma ray or maybe X-ray detectors to catch the electromagnetic signals. So the problem becomes from the electromagnetic side. And why did I say that? Because low luminosity gamma ray bursts are considered one of the primary candidates of the ice-cube diffuse neutrino background in some intermediate energy range. So if that is true, the neutrinos from that source has been detected, but the electromagnetic field, the electromagnetic radiations haven't yet. So in that case, we need a better gamma ray monitor instead of the neutrino detector. Okay, it's almost the time. I go to the summaries. The multi-messenger detection with neutrinos is very significant for differentiating GRB prompt emission models. And right now, the neutrino flux associated with GRBs is over anticipated, I guess. And we're looking forward to advanced neutrino detectors in the future. And meanwhile, we should also focus on the electromagnetic signals from low luminosity gamma ray bursts. Right now we have a lot of sensitive X-ray telescopes. So maybe in the future, if we have a good sample of this kind of sources, then we can still do the stacking process and find the association neutrinos. Yeah, thank you.
Thank you very much, Shunke. Questions?
Since you mentioned that there also some gamma ray, X-ray signal can fall into the MeV range. So right now in the community there's some like proposal like filling the MeV gap by some proposed future, like VLAS in China, or also like CubeSaw in MIT. Do you think they will improve the observation of GRB?
Yeah. So right now we have Einstein probe. It was working on the KeV band, but with a very large field of angle. It's already in operation and have, as far as I know, it have a lot of X-ray transient samples. Maybe most of them comes from this. I guess we need to check their archive carefully. But the problem is, even they have this, they have these signals, they cannot do the stacking and analysis of neutrinos because they cannot access the ice cube data. So if they have a good sample and they can assign some neutrino data, then doing this would be very meaningful. And for another one, like the swarm, is something like Swift telescope, but is maybe have a more higher sensitive and can monitor the all sky gamma rays and together with X-rays. And also together with optical, they have optical telescope on site. So yeah, there are a lot of ongoing programs to do that, and they have already found a lot of very interesting samples.
Okay,
Yeah.
thanks.
Yeah, thank you. I was just wondering, could you have multiple of like these models working together, like the dissipative or also like the internal shock model? Or can you really use the neutrino flux to exclude certain models from?
You mean in one specific source or for different
one
sources?
specific jet like GRB.
One GR.
Or like
sorry.
even through, I can imagine like you expect also through the stacking, right? To also that
Yeah.
all the GRBs, even though you stack them, have the same model.
Yeah.
But could you have multiple models like?
That's a interesting question, because theorists don't like multiple models. It's at least one model should dominate, but of course, from the logic, your proposal cannot be ruled out. It's very it's yes, likely they have both because for the a lot of gamma bursts, they have both the thermal component and non-thermal components. Maybe they just comes from a different mechanisms, and but theorists don't like. You can argue, but they prefer some models to be dominant.
Yeah, if I may add to that, I think, for example, the internal shock scenario, working together with the ICMART scenario might be difficult, in a sense, because internal shocks require that the jet outflow is kinetically dominated, so you don't have strong magnetic fields, whereas the ICMART scenario, which takes place at larger radii, requires to have high magnetization still, so you cannot have both happening. But it could be potentially possible to have dissipative photospheres plus some kinetic models like internal shocks.
Yes.
But it's very difficult to differentiate then, because you start with just one idea, you rule it out, and then you move to more complex scenarios.
And simulations has found internal shocks and magnetic reconnections as below the photosphere, and there's no reason this effect disappear beyond the photosphere. So for that two models, it's okay to have both, but for ICMAT, yes, they should be magnetic dominated, and they don't have a very strong internal shock.
Actually, also, yeah, to Maria, like, because could these like information on these type of jets also say something about the active galactic nuclei? Like if you can rule out, let's say, the most expected flux from dissipative models and stuff, but only, let's say, you're only compatible with ICMART.
That's a very good question. I think you cannot take the results from the GRB analysis and extrapolate it to AGN, because you have different photon fields, you have different densities. So the neutrino spectrum is also related to the photon fields that you have available. And here you are dealing with a very different photon field compared to AGN. And AGN jets are typically also less dense, I would say, compared to GRBs.
Yeah, thanks for the talk. I was a bit puzzled. You said that KM3net is better than IceCube Gen 2 when it comes to this magnification. And of course, I'm part of IceCube and I feel now very worried. But how does it come that in your... So you had this one plot where you showed magnification 10 for KM3net and IceCube Gen 2 was 8. I saw the factor 8, I understand. This is kind of like the larger volume. But why is KM3net so good here?
So which one is overestimated? Chemistry is overestimated,
So you
or
have
the
here-
ice cube
So
2
you, so you have here IceCube Gen 2 at 8 and KM3net as at 10.
maybe, yeah. It's maybe I'm wrong, but from your point, well, which one is, because ice cube generator 2 is underestimated or chemistry is overestimated?
Yeah, I mean, you're comparing to the effective area of IceCube, right?
Yes.
And I would expect that KM3net would have a magnification of 1 because it's about a cubic kilometer detector if it's fully deployed, but not a.
Is the same as in the sea or in the ice is similar?
Yeah, of course, there are differences with respect to angular resolution, for example. But I think for GRBs, what's most critical is that you have like the temporal correlation. So I guess angular resolution might not play such a big role here. But
Okay.
yeah, I mean, okay, this is not from your work, right? No, it is actually.
It's-
Yeah. So, sorry. It is.
Yeah,
So
we found the sensitivity curve from some
Okay.
literature, and I can check the paper.
Maybe we talk about it later. Yeah.
But anyway,
Okay, there's the one.
it's good to know.
All right, so as someone who worked on both experiments, one gigantic difference between KM3net Arca, which will here probably be the important one, and IceCube Gen 2 is the spacing between the different strings. So I think the energy resolution in KM3net is a little better because the strings are closer to each other. That might be interesting. And then Gen 2 radio doesn't really contribute, right? Because the energy range at which the GRBs
Just the in-ice volume should be 8 times larger than IceCube.
This is
how I read this factor of 8 here, but
well, I think here it's only this. I think I'm not really sure about the Gen 2 value here because I did look at the effective area of Gen 2 in ice with the toys software at some point, and it was also just a factor of 4 to 5 bigger, which is also the value that Morase et al. Usually use. It's
in terms of sensitivity, so sensitivity we aim for 5.
Yeah.
But this is more like what type it's emission. Yeah. So I guess here you have very low background, so you can probably scale.
that's probably fair, yeah.
Sorry, this is not way.
Yeah, sorry.
Oh, yeah. Thank you. Thank you for the comment.
Any final question? If not, we'll thank Shunke again.
Sorry, not computer.
Yeah, maybe you.
Yeah, this